All right. Good afternoon, everyone. I'll begin with a kind of simple analogy. Sometimes it's good to have different zoom levels. If you want to know what state you're next to or states, the map on the left tells you very clearly. If you were to try to figure that out with the map on the right, you'd have to pan over really far. But if you want to know what lakes and sounds and whatever else you're next to, maybe the zoomed in one gives you a more obvious picture of that. And so this is, in part, a story of how I'm using QEMU as one of those zoom levels for figuring out computer architecture questions and software analysis, software optimization questions. My name is Christopher Covington. I'm employed by Qualcomm Innovation Center, Incorporated, also sometimes doing activity through Linaro, through an arrangement there. I'll be talking today. I'll give some brief definitions, background, where I'm coming from, definition of things that are not common, in my estimation, in the QEMU, KVM world. I'm going to discuss a number of mostly forks that I've encountered of QEMU that took the code base and did neat things with it. And then I'm going to kind of cherry pick some of the use cases they implemented, talk about how I use them, why I think they're useful, and I have implemented a number of these, or me or colleagues, and sent them out as patches. But I think it needs a lot more work to really get into the right shape. And during the use cases, I think it'd be most useful to attack each use case as we go with discussion. So I'd welcome that. So I mostly come from an ARIC64 background, started with that out of college. If I use weird terminology, that's why. So also, when you're trying to figure out what the best microprocessor design to implement is, you need lots of different models, and some of them are fast, some of them are really, really, really slow. And so starting with the fast ones, you have functional models like QEMU that operate on sort of a ISA level, instruction set architecture, that they can count instructions, but they don't really have any clue what a real cycle count would be. A timing model tries to figure out that cycle count, maybe approximately. And then you might simulate your Verilog or your VHDL, and that's probably the really slowest thing, but I mention it because I try to run stuff like that sometimes. CRIU, Checkpoint Restore and Userspace, is a neat little project. It's kind of like VM snapshots, but you don't have to have a VM. You just have to have Linux. And so I use that. Also, I forgot to put on this, but I'm mostly using QEMU, or right now I'm only using QEMU in TCG mode. It'd be interesting to do some of these things with KVM, perhaps, but maybe I haven't thought through how to make that all work. And then this fast-forwarding thing, I define it as dumping a checkpoint on a fast system and restoring it on a slow system. So if you're able to run in a function model orders of magnitude faster than your timing model or your HDL simulator, run up to the middle of the program and dump a checkpoint and then restore that checkpoint on one of the slower systems, you have fast-forwarded through that first half of the program's execution. And so, first of all, thank you to everyone who has worked on QEMU and made these kinds of forks possible, made the regular use cases possible, made my work possible. It's really great. These are a handful of forks that I've come across, and some of them I thought, gee, wouldn't that be cool if I could do that thing, but they forked off QEMU before it got ARIC64 support. So I can't use it out of the box. So I don't have a solution to people forking QEMU and then the functionality doesn't get upstream, but maybe for the things I care about, I can try to help things lean in that direction. So imagine we have a really long program that we want to run. We want to study it. Maybe we want to study how a CPU implementation executes that workload. Maybe you want to study how you might be able to write a better compiler to make it work better. But it's really long, and it kind of has these different phases, different colors representing different phases. If it's too long, well, let's do that fast-forwarding thing and chop it up. And if you're able to do a bunch of those, you can, in this little example, we reduce the execution time by 8x. And you're still doing the same amount of work, but you're able to parallelize it. And that's nice. Because your wall clock runtime from beginning of simulation to end of simulation is so much faster. So in order to do this, we need determinism. We need checkpointing to actually work. In practice, these assumptions aren't met perfectly, but they're met well enough for things to mostly work with reasonable error. So this is how I do it in QEMU. So I run in QEMU, and I have a little program that will wait a certain number of instructions, usually denominated in millions of instructions. And so I start a Linux process, and I run it. And so in QEMU, this is full system emulation, TCG mode, like ARC64 on x86 64 host. And I run some long-running application. I wrote this little command called ptrace-wait. It just counts instructions. And when the instruction count is expired, it stops the process. And then I use CRIU. CRIU saves the application state to a pile of files. And then on some other model, I can restore it, start up some, record the IPC with perf or something like that, run it for that interval that, it's only responsible for maybe 1/8 of the overall execution. So I don't want to have it run the whole time, but that's the basic flow. And here I'm using architecturally executed instructions as a basic unit of measurement. There can be other ways to count. You could count blocks of instructions or function calls, but this is kind of a nice, easy one. So it's the one we ended up doing. And what are the requirements for getting this to work on QEMU? We need the performance monitors to work and count instructions properly. And currently, that's not all in Upstream QEMU. We have some patches. Hopefully, we can get them into the right state for merging. But if anyone has, insights on maybe there's just a better way to do this entirely, or out of curiosity, does x86 count instructions correctly, or PowerPC, or anything else, or would this be useful for like other use cases? But we can also do better than just parallelizing brute force. If you kind of sort these by color, you can see that some of them are basically exactly the same. And if you uniquify them, then you have less work overall to do. And that's nice. It's kind of like, in my mind, I think of it as running a lossy compression algorithm on the instruction stream that you're executing. So there are different ways to do this. Sometimes one approach is kind of statistics-based. The other is machine learning, k-means clustering-based. But both of them require more than just the ability to count instructions and get it to interrupt when a certain number have happened. So they need control flow tracing. So this, in addition to helping out those sampling methodologies, it can give you kind of that zoomed out view of a program. You're not counting in units of time, nanoseconds or whatever. You're not counting in CPU cycles, but if you don't mind counting in instructions, you can get some useful information about the software you're running. The Simport, the machine learning sampling methodology, uses these things they call basic block vectors. They don't really have to be basic to work. They can just be blocks of some kind. But they're basically a histogram of the control flow. You take every address, say the address of every branch you see, and whenever you encounter it, you increment its count by the number of instructions since the last branch, and then every time you see it, that keeps accumulating until you get to the end of some fixed length interval. And these histograms allow you to compare phases and sort of detect when you have the same colors. And the exec disassembly dumping debug option gets most of that information out to a command line user of QEMU TCG mode. But it'd be nice to know the exact length of a block, including if it's partially executed or if there is a circular link, how many iterations that goes through. And I think so. There is this Icount mode, which has some of this information already. And please feel free to correct me if I'm wrong. I'm sort of a user trying to become a developer in order to do these cool things. Yeah, I think eventually, so I always think of two kinds of interfaces. There are external interfaces that if you are dealing with a hardware machine, you would have to hook up like a JTAG debugger to work with it. And there are self-hosted interfaces that you can do from within the kernel, within application software. You read some registers, poke some memory, stuff like that. And so I think ideally you might have both interfaces available. Something external, you just run QEMU, you dump it, and you get the information out on the host. But if the guest wants to take care of this kind of thing itself, that's good because in the end, if you're only looking at one architecture, a self-hosted interface is portable across all the simulators that choose to actually implement that much functionality, and also hardware and FPGAs and stuff like that. So using what the hardware does is great for portability. And where architectures differ, maybe we have some nice abstraction layers in the kernel, like the perf events open system call. So yeah, if anyone has thoughts on better ways to do this, or if this is already there and I'm missing it, or if there are other reasons to want this, I'd be interested in hearing. And so diving into even more detail, so control flow is program counter addresses. Memory accesses are whenever you have a load or store to or from memory, what is the value? What is the address, virtual address, physical address? And so what can you do with that? You can drive a cache simulator with it. That's kind of interesting. It's a timing model that you don't really need a real CPU to model some things at that order of magnitude. And another use for it is, so I've talked about these application-level checkpoints with checkpoint restore and Userspace. This is a different kind of checkpoint that I've been using a little bit recently, and it's an ELF. It's a binary that restores itself. Running the full thing would do that too, but this is if there are ways to sort of ignore the first 5 writes to a memory address and only take the 6th, because that's where you're starting from, then you can skip a little bit of work there. So self-restoring checkpoints, you would like to be able to see, at least I think in this paper and in the way that I've done it, it's only meant to run for a specific duration. And so you'd like to see what accesses actually occur during those several million instructions, and only checkpoint those and only restore those. So yeah, if you had memory access tracing, you could create these little ELFs that you could load and they restore all their own state, and they run, and they're done, and they're pretty. I found them to be useful in some situations, although it's a bit of a niche. And so I think here the requirements become more invasive. Read or write, yeah, no biggie, but you want both the virtual and physical addresses of the guest or target and the value. And I actually have no idea whether QEMU has this already. Again, if it could be, yes, Paolo, please.
So that it doesn't. Try to get the request working every other week. On the other hand, there is already very good tracing mechanism, and there is something that I don't know exactly the details of to do the tracing from the CG code. So to add the traces, the codes to the tracing function only if they are actually required and not the traces are labeled. So basically it's just a matter of adding the required breakpoints and generate codes.
Okay, thank you. Yeah, that sounds great. I don't know if the recording got that, but he was just commenting that the tracing infrastructure has ways to work inside TCG and in a nice, only on when you need it kind of way. And that sounds quite promising for implementing stuff like this. Thank you. Yeah. And so this is a little bit speculative, but I was thinking the other day, what if user mode, QEMU, checkpoint restore in Userspace, and these kind of self-restoring checkpoints could interoperate? I don't know if it would be kind of like a Babel checkpoint conversion tool or however it might be implemented. But it seems like that might be kind of interesting, at least as a thought experiment. I thought I'd throw that out there. Yeah, I'm afraid I whizzed through my slides much faster than I anticipated. But any questions or comments? If you happen to be curious about CRIU and ptrace-wait and so forth, I'll be diving into a little bit more detail at the Linux Plumbers CRIU micro conference tomorrow. It starts at 1:30, but I'm kind of near the end. All right. Thanks.